Hello, so in this video we will talk about the so-called vector product, or which is also called the cross product. So the definition goes like this: we have a vector A and we do the vector product, so it is represented by this symbol. If we do A cross B, so this is given by A2 B3 minus A3 B2, A3 B1 minus A1 B3, and A1 B2 minus A2 B1, where this is the X component, this is the Y component, and this is the Z component. So if I is the unit vector in X direction, so it's represented by this. Similarly, J, this is the unit vector, and K, this is the unit vector here. Then we can also use the determinate notation. Now note that this is actually not a determinant. Why? Because these are scalars and this is a vector. Okay, so in principle this is not a determinant, but what we can do is we can use this notation to expand this guy to reach this guy. So we'll get something I plus something J plus something K, and this one, this is equal to this guy, and this is equal to this guy, and this is equal to this guy. Okay, this is what we are trying to say here. Okay, and if you expand it, so expand, the best way is to expand using the first row. Okay, now first of all, what we want to prove is we want to say that the cross product of A here, so this is not a, but this is the vector A, so is with itself is 0. So what we want to say is A cross A, this is equal to the null vector. So when I write underscore under a symbol, it means it's a vector. Okay, so if we do that, then what we have A2 A3. So all we have to do is replace these B's by the corresponding A's. Minus A3 A2 comma A3 A1 minus A1 A3 comma A1 A2 minus A2 A1, which is equal to 0 0 0, which is equal to the 0 vector. Okay, because this cancels out with this cancels out with this cancels out with this. Okay, so here. Okay, so then this is proved here. Now what we want to prove is that A cross B is orthogonal to both A and B. So in other words, what we want to prove is the scalar product of A cross B with A will give us 0 vector or 0. It gives us 0 because scalar product will always give us a scalar. Okay, no vector here. So this is a 0 number here. So then what do? We have A cross B is what? A cross B is, again, just writing it down like that, we will get A1 A2 B3 minus A3 B2 comma A3 B1 minus A1 B3 comma A1 B2 minus A2 B1 dot product with A1 A2 A3. Okay, so this is equal to, so how do we find the dot product? We say this guy times this guy, and this guy times this guy, and this guy times this guy, and then we add. Okay, so I will add it in the same step. So I'll write A2 B3 A1 minus A3 B2 A1 plus A3 B1 A2 minus A1 B3 A2 plus A1 B2 A3 minus A2 B1 A3. Correct? Then let's see what cancels out. So we have A2 B3 A1, then A2 we don't have it. A2, so A2 B1 A3, this guy cancels out with this guy. Correct? Okay, then we have A1 B3 A2, so this goes and this goes. Correct? And then we have A1 B2 A3, A1 B2 A3, so this goes and this goes. So the answer is 0. Okay, so this is now proved. Okay, now we come to this guy. So now what we want to say is, what we want to prove is that the magnitude of A cross B, this is equal to the magnitude of A times magnitude of B times sine of theta, where theta is what? Theta is the angle between A and B. Okay, so for example, if we have, this is my A and this is my B, this is my B, and this is theta. So then magnitude of A times magnitude of B times sine of this angle gives me the magnitude of the cross product. Okay. Okay, so let's start by proving it. So now we will start like this. We'll say A cross B squared. Okay, so we'll start by A cross B magnitude squared. So this is equal to what? This is equal to A cross B dot product with itself, correct? Okay, so this is the property from the dot product here. So then this is equal to what? This is equal to, oh, this is a long algebra here. So I just have to repeat this guy here. So A2 B3 minus A3 B2 comma A3 B1 minus A1 B3 comma A1 B2 minus A2 B1 dot product with, so the same thing here. Okay, so this is equal to what? So this is equal to, so if I multiply this by this, so I have A2 B3 squared plus A3 B2 squared minus 2 A2 A3 B2 B3 plus A3 B1 squared plus A1 B3 squared minus 2 A1 A3 B1 B3 plus A1 B2 squared plus A2 B1 squared minus 2 A1 A2 B1 B2. Okay, okay, now let's combine this and this. Okay, so this I can write by some algebra here. What I can write it as A1 squared plus A2 squared plus A3 squared, not squared times B1 squared plus B2 squared plus B3 squared minus A1 squared B1 squared minus A2 squared B2 squared minus A3 squared B3 squared, and then minus these terms which are left. So 2 A1 A2 B1 B2 minus 2 A1 A3 B1 B3 minus 2 A2 A3 B2 B3. So this guy is what? So I can write it as A1 so now before we do that, so what is this guy? This guy is what? A squared vector. And this guy is what? This guy is B squared. And this guy I can write it as A1 B1 plus A2 B2 plus A3 B3 squared. Okay, so then this is what? This is the scalar product of A and B, so I can write it as A squared B squared, so I can write it as A B, which is equal to A and square, of course square here. So A squared B squared minus A squared B squared cos theta squared. Okay, this cos theta, this modulo sign is not necessary, but we just put it because it does not make a difference. So I can say A squared b squared 1 minus cos squared theta, which is equal to a squared b squared sine squared theta. So then this guy is equal to this guy. So this means that this is, if you take the square root, so here, okay. Okay, so this is about this part. Okay, now we are interested in a distance of point R to a line L. So let's say we have a point here which is R, and we have a line like this. This is my line L. Okay, now we have 2 points P, let's say P and Q on this line. So we have, let's say we have 2 vectors here. We have this vector and we have this vector. This PQ is on the line and PR is joining P to the R, and R is the point we are interested in. Okay, this is theta here. Okay, now we are interested in this length. Do you agree? So this is the D we are interested in. So by this basic trigonometry, what is D? So what is D? So D, this is equal to the magnitude of the vector PR times sine theta. Do you agree? This is correct, right? We also know that if we take the cross product of this one, so if we say PR cross PQ, this is equal to what? We have just seen that this is equal to PR PQ sine theta. Okay, but this part and this part combined, this is equal to D, correct? Because we have just seen it here. So this is equal to D times PQ. So D is equal to actually PR cross PQ divided by PQ. Okay, so this is the way we can find a distance from a point to a line using only cross products. Okay, now for that line we need to have a vector, and we need to have a vector from that point of interest to any point on that line. Okay, geometric interpretation. Okay, so for geometric interpretation, what we are interested in is we will be doing 2D and 3D. So for two-dimensional, we have this situation. We have a vector, let's say A is like this and B is like this. So this is my B and this is my A. Okay, now we want to show that this and this represents area of parallelogram whose adjacent sides include vector A and vector B. Okay, what we mean is that if we do this, so if we say this is my P, this is my Q, this is my R, this is my S, so we want to find the area. So what is area of parallelogram PQRS? This is equal to length of the base, which is length of B, times the perpendicular height. So perpendicular height is what? So perpendicular height is, let's say this is H. So times H. So but what is H? Using this, if this is theta here, the angle between A and B, what is H? H is nothing more than A sine theta. So B A sine theta, and we know that this is equal to A cross B, the magnitude. Okay. Okay, so this is the way to show that this is in the 2D. Now we talk about 3D story here. So if we have 3D story here, then we have a parallelepiped. Okay, so for example, this is my A, this is my B, and let's say this is my C here. So this is my A, this is my B, this is my C. So A, B, and C here. Now this is the parallelogram. We know that this is, so area, so what is the volume? So this is equal to area of base times perpendicular height, right? So perpendicular height, correct? So area of base we already know, this is equal to A cross B, okay? But what about this height? So for example, if we are interested in, let's say, now this goes like this, this goes like this, this goes like this, and we have this situation. So what is a perpendicular height? So perpendicular height is this one, right? So this is my perpendicular height. So this perpendicular height, and with what angle are we talking about? We are talking about the angle which C makes with the vertical here, okay? Why? Because A cross B is in this direction, and we are interested in this angle. So this is my here theta. So again, so A cross B is always perpendicular to the plane where A and B are, okay? And C makes an angle theta with that one, right? So then this means that the perpendicular height, this guy, this is equal to C times, so magnitude of C times cos of theta, okay? So then what do we get? So this is like this. So times what do we get? We get A cross B times C times cos of theta, okay? Now this cos of theta should also be like this. Why? Because this angle can be more than 90 degrees. If this is more than 90 degrees, we'll get a negative cos of theta, and we don't want that, okay? So then what do we get? We get this is equal to this and dot product of this. So we can get A cross B dot product with C, okay? So this is what? This is the volume of a parallelepiped, okay? So our last problem for this part is that we want to prove that A cross B scalar product with C cross D, this is equal to this determinant here, okay? And we will use this property. How do we get this property? We can use our algebra, our basic definition, and do lots of lengthy algebra to prove this. But you can actually check whether this is true or not, and any text of vector product, you will see that either they have this as a theorem or as a corollary or something like this, okay? So I will assume that this is known, okay? So here we have to use another property. The other property is that if we have A cross B cross C, this is equal to A cross C, A dot C with B, and these are all minus A dot B dot C, not dot, sorry. So this is what we have to use, okay? So there are two things I will use. So now let's start. So then this guy is this guy. So what we want to do is we have A cross B dot C cross D. So A cross B is right here, but C is replaced by C cross D. So I have to replace it by C cross D here. So so this becomes B cross C cross D. Now use this thing. So I will get B D C minus B C D. So there is no dot here, okay? Now this is a dot product, and this is a scalar here. This is a dot product here, and this is a dot product is, you can distribute it here. So you can say A dot C times B dot D minus A dot D times B dot C. Okay, so then this is equal to right hand side, this is equal to this guy here. Okay. Okay, so this is it about some problems which can arise in vector products and how to manipulate different components of vectors to prove several problems regarding vector product. Hope it was easy to understand, and thanks for watching. Hope you like the video.